Thank you very much for introducing me and for inviting me here. So, as you heard, I was also an undergraduate here. I was class of 96. So given that many of you were class of 95, it must be that I was in some of the same classes with you. So it's a special honor to tell you a little bit about what I've been doing since. So first of all, I'm a bit of an outlier on this panel in the sense that I don't work on privacy, at least not explicitly so. What I do work on is physics. Nevertheless, the physics that I love to do the most is whenever we discover a new piece of physics, we ask ourselves, well, if it's truly new, it should be that there are some exciting applications that it could enable. Perhaps they're remote, but there should be. And so we always ask ourselves, what are those applications? And to the extent that it's feasible, we try to pursue them. So today I'll tell you a few examples of that, including security, energy, displays, and also privacy. So first of all, most of our work is in the field of nanophotonics. So nanophotonics is a subfield of nanotechnology that deals with photons, with light. And what we do in nanophotonics is we create these artificially created materials which are structured at lengths substantially smaller than the wavelength of light. So when light propagates inside of them, it cannot really resolve the structure. It looks to light as if it's propagating in uniform materials, but in which the laws of physics have been dramatically modified compared to what they would be in the bulk. And by tailoring the nanostructure, we can tailor the laws of physics, at least as far as light is concerned, almost at will. So let me give you an example that illustrates that approach of something that we did recently. So if you think of any beam of light, very fundamentally, it has exactly three fundamental properties. It has frequency or wavelength, it has polarization, and it has the angle of direction. If I tell you these three properties, I've completely described your beam of light. And while we have great material systems that allow us to discriminate light strongly based on wavelength, so for example, if I want to have a material system that would let red light through and blue light through, but reflect green light, I have many material systems that will enable me to do that. For example, I can have red filters, blue filters, green filters, and so on. If I want to have a material system that allows me to discriminate light strongly based on polarization, so one polarization makes it through, the other one is completely reflected, I can use polarizers like your sunglasses. But we have much less material systems that allow us to discriminate light strongly based on the angle of propagation. So for example, if I want to have material that would reflect light coming at one angle and another angle, but let this light through, I have much less material systems that allow me to discriminate light strongly based on that. An indication, if you think of this as building blocks for controlling light, the fact that we are lacking one of the building blocks to control one of three fundamental properties of light is an indication that if we did have it, that it should enable at least some of the interesting applications. And indeed, that's actually well known. Let me illustrate it on, perhaps it's easiest to understand it on the application of solar thermal energy conversion. So what you do there is you have many of these mirrors which reflect light to this object, heating it to pretty high temperature, and then you convert heat from that into electricity in one of many different ways. In our case, we heat up a nanophotonic material which heats up to pretty high temperatures, like 1200 Celsius. So when you heat it up to that high temperature, it starts glowing. That is, it starts emitting light in all different angles, and that presents losses. In our systems, these losses can be 20, 30, 40%, or even larger. And this is quite fundamental. So there seems like it's hard to deal with, but imagine that if I did have an angularly selective material of this type, then all light coming from the sun, it comes at one exact angle, so that would make it through. But when this thing starts glowing, only a tiny portion of the light goes exactly back towards the sun. Most of it goes at other angles, so that means that that light would be trapped and thereby enable something that we consider to be perfect solar light capture, which is then of use for any solar thermal conversion. It's also potentially useful for conventional photovoltaics because their large part of the losses has to do with radiative recombination. Detectors, cameras, because when I'm trying to take a photo, I'm interested only in signal from one direction. All other directions present noise. Privacy cameras, I'll say a bit more. Privacy screens, I'll say a little bit more about it later. So let me show you something that we did recently. So remember, what we're trying to do is something that would look like, when I look at it, it would look as a mirror. Then I tilt it, it still looks as a mirror. Then I tilt it, at one angle it looks as a window. And then I tilt it again, and it looks as a mirror again. So here is something that we did recently. So here you see our quote-unquote mirror and reflection of iPhone camera in it. We put an object behind it. Now I'll start rotating it, and it'll reflect objects in the lab, in particular this ruler that you see here. So you see now it acts as a mirror. Now it still acts as a mirror, still acts as a mirror. And then at one particular angle, it's completely transparent as a window. And then we keep tilting it again, and it looks as a mirror again. So to emphasize, when we plot it on wavelength versus incident angle, you see our entire visible range, so from 400 to 700 nanometers. It's exactly and only this angle that makes it through. This is nearly 100% transmission. Actually, here it's about 97%, while other angles are very strongly reflected. And one of applications where that it could be interesting is, as you know, there are these like privacy protection screens which you put on your phone, and when you put them on your phone, then you can look at it head-on, but when you tilt it, people that are looking at it at an angle cannot look at it. And the reason why most people don't like this is because they're right now about 50% transparent. So largely because of that fact, they have only about 0.1% market penetration rate. So having transmission as high as close to 100% is quite important for these applications. Now, when in our work, we have this blessing that I work with Maxwell's equations, and Maxwell's equations are scale invariant. So what that means is that the same physics applies over a huge range of scales and frequencies. So for example, we do work anywhere from megahertz to gigahertz optical all the way to gamma ray. So the materials are very different across all these scales, but the equations are the same. So inspired by that, then in early 2000s, I became aware of one problem that became actually quite rapid at that point of time, and that is, you see, I really love my wife, but she just can't remember to charge her cell phone. And in early 2000s, we had this old Nokia phone, and when its battery was dying, it would make this really loud and unpleasant noise. Now, needless to say, this always happened in the middle of the night. So one night at 3 a.m., it occurred to me, wouldn't it be great if this thing could take care of its own charging? So I started thinking, okay, which physical concepts could enable something like that? And at the time, because it was always sitting on a kitchen counter, so there was always electricity within a few feet away from it, but somehow it just wasn't enough to enable this wireless power so the thing could take care of its own charging. So at the time, I was working on nanophotonic resonators, and that are evanescently coupled. It turns out when you scale up their physics to megahertz frequency regime, or wavelengths which are of order of tens of meters, then you can enable something like this. So this is a photo from 2007. So what you see here is an electromagnetic resonator which acts as a source, transferring power wirelessly to this object here, lighting this light bulb. This is the team that executed this work. You will notice that we are completely obstructing the direct line of sight between the source and the device, but the wireless power doesn't care. And most importantly, you'll notice that we are still smiling. So encouraged by this, we started a company that in 2007 that aims to enable wireless power over a wide range for a wide range of industries. So these are some of our collaborators and some of our licensees. So for example, Toyota is very interested that now you have this plug-in Prius or you have electrical car. Whenever you come home with it, you have to remember to plug it in, and in the morning you have to remember to plug it out. So compared to your neighbor that has a regular car, it looks quite a clumsy experience. But so imagine that one day in the future you drive into your garage and the thing takes care of its own charging. At that point, if you compare your car experience to your neighbor's, the only thing that you'll notice is that you never have to go to a gas station ever again. So at that point, it becomes actually much better user experience. Then so Toyota licensed our technology recently with motivation like this. Then Intel that has more to licensed our technology also that has more to do with consumer electronics. So the original motivation. One I'm particularly interested in has to do with medical devices, in particular implanted medical devices. So there'll be much more and more of them as we go along. So the current ones like pacemaker and so on, they consume only very little power, so they can rely on a battery for a long time. But as we go along, there'll be opportunity and desire and need to put more higher and higher power devices. So for example, this company Thoratic that licensed our technology, they do ventricular assist devices or heart pumps that require about 5 or 20 watts. So for example, Dick Cheney had one of their devices before he got a heart transplant. And there you cannot have wires sticking out of the patient because they're a constant cause for possibility of infection, so you have to have a way to do this wirelessly. So they would like to do this for the next generation of their products. And then there is a wide variety of applications in security, for example, for recharging these autonomous robots. So I actually brought a little demo to show you. Can you please dim the lights a little bit? So this demo, the only purpose of the demo is actually it's a scaled down version of the photo that I showed you. So the main purpose is just to demonstrate how it works rather than serving any useful purpose. So this is a source of the electricity. It has one of our resonators inside it. And this is a device that doesn't have a battery, but it does have one of our resonators. So when I bring it some distance from the source, you can see how it will light up irrespective of the position and the orientation. And most importantly for us, it also goes through objects. So our former CEO, actually, he went to Harvard, and most of us went to MIT. So we always have this MIT-Harvard thing going on. So whenever he would do this, we would love to point out that in his case, it doesn't prove anything, because there's because there is nothing there. We can bring up the lights now. Thank you. So let me shift gears a little bit and tell you a little bit about transparent displays. So this is another example that when we started with this, we did not have a project working on transparent displays. We were working on something else that I'll tell you about shortly. But as I said, we always ask ourselves what are other interesting things that we can do with the things that we already have. And the thing that we were actually working on, substantially different, actually has to do with privacy for soldier. So, you know, there are these smoke grenades, especially if you like action movies. So when a soldier gets in trouble, he or she explodes one of these things in order to provide some privacy, security. So when you think about what is an optimal smoke grenade, so you would want a smoke grenade to be as small as possible and as light as possible, so the soldier doesn't have to carry much weight. But when it explodes, it makes as big cloud as possible over as wide range of wavelengths as possible. It turns out that is a perfect application for nanophotonics because, for example, it's well known that when you have a resonant nanoparticle, which is substantially smaller than the wavelength, then it can, although its size is much smaller than the wavelength, the cross-absorption area that it presents for incoming light is actually as big as lambda squared because it sucks in all this energy into its own near field. So basically, although its size is much smaller than the wavelength, it can absorb much more than the wavelength. And this way, we predict that we should be able to reduce the weight of smoke grenades by about a factor of 30. So that means soldiers will have to carry much less weight in terms of smoke grenades. Since we were already working with these nanoparticles, we asked ourselves what are other interesting things we could do. It turns out that transparent displays are one of them. Let me tell you how, but first let me tell you why would you be interested in transparent displays. So there are many potentially very interesting applications of transparent displays. So a number of companies are working on them now. They're not quite there yet, but they will be there soon. I'm convinced in 10 years you will see them almost everywhere. Some sooner, some later. So one of them has to do with this heads-up display. So basically, it projects some elementary information for you when you are driving a car or airplane, so you don't have to look down when you are driving. Then there are windows of shops, Google glasses, and finally, action movies. So these days, it's actually pretty hard to find an action movie that doesn't have transparent displays in them. That's a good indication they'll hit the market some 10 years later, right? So how do they work? Well, this one and this one, they work based on partial reflection. So basically, you have a glass, you put projector below it, and then most light makes it through. Only part of light goes back to you, but it's sufficient to see something like this. Now, you can immediately see that's going to have a narrow viewing angle. And that's OK because, you know, for an application like this, when you're driving a car or an airplane, hopefully you don't move your head too much, right? But it's completely unacceptable for application like this or like this because consumer has to be able to see it from any angle. So this one and this one, there are many approaches that people follow. Perhaps the largest pushes in this thing in transparent electronics, like transparent OLEDs. As you know, OLEDs, even when they're not transparent, they are pretty expensive. So this is a very promising approach, but I think it'll take them some time to get there in terms of price. And I'm still trying to figure out how this one works. Fortunately for me, it turns out that Tony Stark, as you know, was actually a fellow MIT alum. So my hope was to use some alumni connection actually to connect me with him so I could ask him. So what was our idea? Well, if you just take a piece of glass and I put a projector like that one and try to project onto the glass, I'm not going to see much. Why? Well, that's kind of the point of glass, right? You want light to get through. But imagine that if inside of the glass I embed nanophotonic scatterers, which scatter light only and exactly at one wavelength. Let's call it blue for now. Then if I shine a blue laser of that exact wavelength onto it, I should be able to make a strong image. But if I just look at that glass, then it should be largely transparent. Why? Because only a tiny portion of light is in that exact wavelength. And then I make one for blue, one for green, and one for red, and I have a full color display. Now, there are many ways in nanophotonics you can imagine implementing something like this. So we are working on a wide variety of them. But as a proof of concept, we took the one that we already had in the lab, and that is a nanophotonic resonant particle. So in particular, the one which you can see it's much smaller than the wavelength, the one that works great for blue. We also have one for green and for red, but the one that works great for blue looks something like this. I would like this to be narrower than it is, and I would like there to be no absorption, so that's something that we are working on. But nevertheless, it was sufficient for us to show a proof of concept. So then we took these nanoparticles, combined them with polyvinyl alcohol, pour it on the glass, and let it evaporate. So what we end up with is a sheet of polymer that has these nanoparticles embedded into it. And this entire experiment cost us $7 to do. So when you do that, then you combine it with a projector. You projector just on a regular glass. You don't see anything. The objects are behind the glass. But when you project onto our glass that has this thin sheet of polymers with nanoparticles in it, you see both the object that you're projecting, and you also see the objects which are behind the screen. So let me just show you a movie briefly how this works. So again, the objects are behind the screen, and I'm making this projection onto the screen. And the projector is, of course, in front of the screen. And just to show the transparency, we'll also remove some of these objects so you can see both the objects and the thing that we are projecting. So as I said, there is, I already illustrated some of them. There is a wide variety of different applications possible. I already talked about some of them, but just to illustrate what is all the wide range of things that you can do is that fairly recently, some guy contacted me actually from Harvard, of all the places, and it turns out that they have a celebration pretty soon. Some important celebration, and he has been put in charge of, actually, his task is to project, during this celebration, project images on John Harvard's statue. Now, it's one of the most touched statues on the world, so it's very reflecting. You cannot project onto it. They explicitly don't allow him to change its color, so you cannot paint it over and then remove the paint later. So his thought was, which I thought was quite creative, is to cover it with our sheet of polymer, which would be very transparent, so he wouldn't change the color. I mean, he could take it off later, and then he would still be able to project on it. So I told him, hey, that's a splendid idea. We can project MIT onto the guy's forehead. Yeah, so he never got back to me. I'm not joking, he stopped responding to my emails. So anyway, I gave you a short illustration of this thing that I enjoy doing the most, and that is doing science, but keeping an eye open for possible applications. And on that note, I would like to share with you a quote that I bumped into some time ago. That's actually now one of my favorite quotes. It's from a guy that's talking about setting up this institution, and the way that he describes this institution is describing, I couldn't do a better job of describing a better dream place for me to work at. I should tell you that this quote comes across a little bit grumpy, but anyway, I'd like to share it with you now. So, the world enforced distinction between the practical and scientific worker is utterly futile, and the whole experience of modern times has demonstrated its utter worthlessness. As I said, a little grumpy, right? In order to be truly practical, we must know the material which we work, the implements which we use, the character and properties and forces of those materials, and the mechanical qualities and properties of them too. And in knowing this, we must be scientific. We maintain that in the school in which we are here interested, we are training men in a preeminent degree, not only to be scientific, but to be practical, and to be practical largely because they are scientific. William Barton Rogers, the founder and first president of MIT. On that note, fellow alumni and dear guests, thank you very much for your attention.